Hello and welcome to this three-part interview series where we're going to be covering qPCR methods for gene therapy bioanalysis. I'm joined today by Kate Veirs, who is the group lead for translational medicine at QPS. Welcome, Kate.
Hi, lovely to be here.
Lovely to have you. So let's kind of start off super broad and talk about each of these three techniques individually. So dPCR, ddPCR and qPCR. Can you give us a bit of a summary of each of them and where you might use one of them over the other?
Yeah, so qPCR really is a quantitative method that uses a single-stranded or a double-stranded DNA template, combining that with oligonucleotides, so two of them and two primers, a forward and a reverse, as well as a probe, which is also another oligonucleotide that actually has a fluorescence and a quencher attached to it. So this reaction, or this qPCR reaction, then goes through a temperature cycling program such that at each stage it goes through denaturation, binding of the primers, and then elongation of the template. And at that, the instrument actually detects the signal of the fluorescence as it is cleaved from the probe itself. So this gives back a value that then is able to be used against a standard curve. So that's one of the things with a qPCR reaction or a qPCR quantitation is that you do need a standard curve, but it does give a high range of assay linearity, so which is great. ddPCR or droplet digital, PCR is a nano level PCR reaction. It also is an endpoint reaction similar to qPCR. But instead of going through a cycle thresholds, you're actually creating partitions using an emulsion and droplets. So the instrument actually will go through and calculate or quantitate the droplets, both negative droplets that don't have your fluorescent probe, as well as positive droplets that do. And then using Poisson distribution, it's able to give you an absolute quantitation. One of the nice things about this is that you don't need a reference standard. You don't need a curve to actually be able to quantitate your samples. And last is dPCR, which is just digital PCR. This uses a similar technology of partitioning, but instead of emulsions to create droplets, you actually use physical partitions. So the plate itself has these partitions. So it's very similar, again, Poisson distribution, negative, positive droplets, and that's how you're able to quantitate each one.
The accuracy, sensitivity and precision that you can achieve on all three of those platforms differs quite substantially. Could you talk us through that a little bit more?
Without going kind of too deep into the weeds, try to keep it entertaining because it's entertaining in all of it. The really the biggest thing in the difference between each of them is really looking at where the places for possible sources of error. So with ddPCR, you are limited by the generation of the oil droplets or the emulsion droplets. So if there's something that disrupts that, it will impact your results. For digital PCR with those physical partitions, you're limited by the number of partitions that a plate can actually be manufactured with. So it's a bit of a limitation, but also something that can be worked around. And then last with qPCR, because you need that standard curve, you actually have to find an appropriate reference standard that you're able to mirror your samples against in order to generate accurate results. All of these, possible sources of errors, there are ways to, work your way around them and actually find solutions to, mitigate against that. So you really have to look at scientifically what makes sense for the platform you're using. Are you able to get the sensitivity you need with the number of partitions? Are you able to create the emulsions successfully? Are you able to find and source enough reference material in order to actually, meet your sample analysis needs?
With digital PCR offering that absolute quantification, do you see the era of qPCR kind of coming to an end anytime soon, or do you think it'll last way into the future?
I do think qPCR is still in its heyday, but I think dPCR and ddPCR are both good platforms to use in the correct situation. One drawback I will say is that dPCR and ddPCR both in cost and in time and money, there is some things to consider when looking at that. So where qPCR is able to do high throughput quantitation in a effective and costly manner. Something you have to think about is having that source of that appropriate reference standard. Where dPCR, ddPCR, while it might be a little bit of a higher cost, you don't have to have that same material. Another consideration when you're looking at these different platforms is, your analytical range. So all of the methods are quite sensitive, but you do have to manage your linear range. So ddPCR or dPCR, you're looking at a much smaller analytical range, where qPCR, you can actually span a much larger range. So it's really kind of more of a targeted approach versus a more wider spread approach.
So following on from what you just said there about this cost element, something that I'm sure comes up quite frequently is this kind of cost to performance or cost to benefit. Upfront costs and running costs, what can somebody expect from these three techniques? And is there a clear winner in terms of that cost to benefit?
Is there a clear winner? Yeah, I don't know. I think it's a conversation that has to be had of what you're looking at. Are you looking at analysis that has quite variable results or variable concentrations? Then a typical qPCR reaction is what you're going to be looking for. You have a large sample count, again, a qPCR is going to be more efficient. In terms of training time, standard qPCR is also kind of where you're more getting your bang for your buck. But, in terms of ability to mitigate not needing a reference standard and having to possibly manufacture something and keeping consistency of quantitation across an entire study, dPCR and ddPCR both have that benefit going for them. Having a very targeted assay range is also a great part of ddPCR and dPCR. Last for ddPCR, dPCR is really looking at the ability for input into the reaction. So with qPCR, you do have to worry about possible PCR inhibition from the matrix or the sample itself. So taking that into consideration, where these other technologies or these other methods are actually able to overcome that, where if you're looking at trying to go as sensitive or as low as possible, even the possibility of doing a direct PCR, not having to do any sort of extraction prior to that, is a possibility that labs are able to use and ensure that they can go as sensitive and as low as possible.
If we focus on digital PCR for a moment, there's some ongoing industry discussion around establishing universal calibration standards, which would enable that kind of cross-platform comparability. I'm interested to sort of get your take on that.
It kind of depends on what you're using the assay for. If you're using it to say that the method is working or that the instrument is working, a universal standard kind of makes sense. But if you're looking more towards a very specific target or a very specific sequence, you kind of will then have to approach a multiplex type methodology or multiple assays in one reaction or one well. And what that can induce additional challenges of, with developing the method, ensuring that you're getting the right sensitivity for both methods. So you still would need that secondary reference, even if you are using universal. It would just help to ensure that the lab to lab performance is consistent.
Brilliant. So we're going to wrap it up for the first part of this series, but definitely stay with us for part 2, where we're going to discuss the applications of PCR methods across gene therapy development.